Module 2, Process Capability, Advanced Approaches, and Statistical Method Selection. Lecture 1, Differentiating Design Specifications from Process Capability. Design specifications and process capability are often confused, but they are not the same. 1. Design specifications. These are the tolerances set by designers or customers. For example, a shaft diameter must be within plus or minus a certain value. Specifications are about requirements. 2. Process capability. This describes the actual performance of the process. It is a statistical measure of how well a process produces output within given limits. 3. Key point. A capable process consistently produces parts within specifications, while an incapable process frequently produces defects. Engineers must ensure that process capability matches or exceeds design requirements. Lecture 2, Extending core material to novel situations. While basic principles of variability and statistics provide a foundation, real-world problems often require creativity. 1. Thinking beyond standard uses. Adapting control charts for non-traditional data. Combining probability models with engineering judgment. Using simulation techniques when analytical solutions are difficult. 2. Examples of extension. In automated manufacturing, sensors generate vast data streams. Engineers can extend traditional methods by applying machine learning techniques to detect variation patterns. In additive manufacturing, variation sources are different from traditional machining, requiring tailored statistical methods. 3. Key takeaway. Engineers must not only apply known methods but also adapt them intelligently to new technologies, industries, and challenges. Lecture 3, Assessing Appropriateness of Statistical Methods. Not all statistical tools are suitable for every situation. Choosing the right method is critical. 1. Factors to consider. Type of data: is it continuous, such as length, or discrete, such as defect counts? Purpose of analysis: are we monitoring stability, predicting outcomes, or comparing alternatives? Complexity of the process: simple methods may be sufficient for stable processes, but complex ones may require advanced techniques. 2. Examples of method selection. For monitoring ongoing processes, use control charts. For predicting future performance, use regression or time series forecasting. For comparing two machines, use hypothesis testing. For identifying hidden patterns, use multivariate analysis. 3. The engineer's role. It is not enough to know how to perform statistical calculations. Engineers must also evaluate whether the method is appropriate, practical, and aligned with decision-making goals. Let us recap what we have covered. In Module 1, we focused on the fundamentals: recognizing variability, identifying its sources, describing it in structured ways, and applying probability and statistics to characterize processes. In Module 2, we moved to higher-level applications, distinguishing between design specifications and process capability, extending basic material to novel situations, and carefully assessing which statistical methods to use for different problems. Manufacturing process and control is about much more than producing items. It is about understanding variation, applying analytical tools, and making informed decisions that lead to consistent quality, efficient production, and innovative solutions. By mastering these concepts, you will be well prepared to design, manage, and improve manufacturing systems in a way that meets the demands of both industry and customers.